Welcome. This is the sketch, organize, solve method for Faraday's law involving conductors and induced fields, in which we have a scalar form of this where we can write it as delta V equals negative n ddt. And then instead of doing the dot product, we write out all of our terms, b of t, dA of t, cosine theta of t. So in our sketch step, we want to draw our magnetic fields and our conductors. And then because we have this time derivative, something in this needs to change in order to induce a voltage. So we want to show a before and after to show how the field or the area or the angle changes with time. And then what we want to do is we want to use Lenz's law to predict the direction of induced fields and induced currents. So in our organized step, we now have this. And so as we were looking at this, we want to determine which measurement changes with time. So this could be b of t, the field. This could be a of t, the area of our conductors. Or this could be theta of t, the angle between our field and area. So we need to determine which of these is in order to then eventually take a derivative. Just so we know, n is the number of loops. And then common dAs are that dA is 2 pi r dr for, again, a circle made of rings. Our dA is the length times the differential width for a rectangle. So now that we have this set up, we can go into our solve. So we want to take an integral to find the integral of b of t, dA of t, cosine of theta of t. And our limits are the conductor's geometry. Once we've taken the integral, then we want to take the derivative. With respect to time. So we're taking an integral over space and then a derivative over time. Once we have that, now we have our delta V is equal to negative n times the time derivative. We can call this the magnetic flux, just to make everything better, and then we can solve for delta V. And then we want to check our solution with Lenz's law. Just make sure that the signs are matching. If the signs don't match, we might have gotten a wrong minus sign here. So we can always use Lenz's law to check ourselves out with that.